Yes. So before, in the process of introducing our speaker tonight, I just wanted to add a few things. Tonight is, unless I'm wrong, tonight is the last Saturday in which we have a public night of our season, and the end of October, and then we start again in May. We're an all-volunteer organization, for those who haven't been here. We're all volunteer. We exist on donations and membership. And we do this because we enjoy sharing the night sky. I mean, it's just the pure love of the science. And we're delighted to have the public come. So thank you for coming, because if you didn't come, we'd be standing here talking to ourselves, because that's what we do. We're standing outside in the dark. What do you think we do? Anyway, the coolest thing about it is we have, if you come here, we have the instruments to capture these photons that have been traveling for hundreds of thousands of light years. And you become part of the phenomenon, because those photons, that bit of energy that came from some of these particles, then strike your retina, and then maybe ignite your brain. You know, so this is the cool stuff. When it's cloudy, of course, we'll have to depend upon this picture. But I just wanted to add this. There isn't anything, I like science fiction, but there isn't anything in any science fiction story that compares to our reality. You know, we have a tendency to just walk right through our daily existence and expect that Walmarts and trees and all that are just like they're supposed to be here. But the very fact that we're in a veneer on the surface of a rocky planet is just remarkable. But I'll give you one example. In 1936, and then I'll introduce, but it's not the end of the season. So in 1936, there was a Flash Gordon movie, and there was a Sky City, they call it. It's an old black and white, okay? In 1980, Star Wars had The Empire Strikes Back, and they had a Cloud City. And you look at that and you say, it's amazing, look at this, a cloud, we'll never have that. I want to point out something. When you walk outside over here and you look up into the sky, there's a huge rock. Don't be alarmed. There's a huge rock that weighs 78 quintillion tons, 8.1 times 10 to the 19 tons. We call it the moon, and it's just floating there. I mean, think about this. We're amazed at this sci-fi movie, but just take a step and we just casually look at this huge rock, 76 quintillion tons. It's just floating there. But weird stuff. The reality is the weird stuff. And that's what we do here. We enjoy it. We enjoy sharing it. We're happy that you come. Keep coming. And we're open for anyone to join or just participate in our programs. Now, we're especially excited when young people are here. We're very excited about it. Thank you.
Especially you.
We're especially excited about that because we want to light up their imagination. This is a way of doing it. And the interesting thing about tonight's speaker is that he, Dr. Mitch Revalski, was one of those kids sitting in an audience many years ago. And now he is a researcher at the, I want to get this right, at the Space Telescope Science Institute. And he was in the audience just like the children that are sitting around you right now.
What's that round of applause?
Now, this introduction isn't complete yet because Keith Marley would like to say a few words about our speaker.
And there you have it. Mitch is not just a brilliant scientist. To NJAA, he's family here. This young man started with us back when he was in middle school and became a QO before I even thought about it. And so he's been doing what I'm doing around here, just talking to people and showing youngsters the space around them. And so I'm just honored to have him talk here again. He's always invited anytime he wants. Sometimes he comes by himself. It's okay. But anyway, I just want to turn this over to Mitch, Dr. Mitch.
All right. Well, thank you so much for that extremely kind introduction. And thank you so much, everyone, for making the time to come out here tonight, right? Everyone's busy. We have a lot of things to do. And all of you took time out of your day to come here and hear about something in astronomy. So I'm really excited to share that with you today. I, without a doubt, have to first give a really big thanks to my wife, to my family, to my friends, to my teachers, to my research team, and in particular, the NJAA. Without a doubt, the NJAA is one of the most important reasons as to why I am an astronomer today, without a doubt. And so the timing is perfect. I'm happy to share that actually, as of this week, I am no longer a postdoctoral researcher at Space Telescope. I am now a full-time staff scientist for the Hubble Space Telescope on the Wide Field Camera 3 team. So, good timing, universe. So, just a huge thank you, a really heartfelt thank you to everyone. I really appreciate everything. With that, let's go ahead and dive in for the night. So, the roadmap, where are we going tonight? The overarching question that we're interested in learning is, how do galaxies and their stars and their gas evolve over time? In order to talk about that, I'm going to talk a little bit about the tools and the techniques that we use to actually study galaxies and kind of give you a little bit of insight to what was already known before we started our studies. Then I'll share a little bit about how we tackled the problem at hand and what we actually found, and then give you a little bit of glimpse into where we're heading into the future. So as astronomers, our most fundamental tool is a telescope. A telescope is a device which is designed to collect more light than our eyes can see and focus it down onto a camera so we can record an image and analyze it later. At the most fundamental level, that's what our telescopes are doing. And there are a few telescopes that are better known than the Hubble Space Telescope. It's been in orbit around the Earth for over 30 years, gathering some of the most incredible images that we've ever seen and giving us insight into things that we had just never seen before Hubble. And so one of those images is the Hubble Ultra Deep Field. This image, taken by Hubble, is one of the deepest views of the universe that we have ever obtained. It required Hubble to cumulatively stare at the same patch of the sky for nearly 11 days. That is 400 orbits of Hubble around the Earth. This is one of the deepest views that we have ever obtained. And the first thing you notice is that galaxies are everywhere. You pick any point in this image and zoom in on it, and it is just filled with galaxies. They're different shapes, they're different sizes. Some are blue, some are red, some are clumpy, some are smooth, but galaxies are everywhere. No matter where we look, we see huge numbers of galaxies. And despite all of their different appearances, they're made up of the same fundamental building blocks. That's stars, gas, dust, and some more exotic things like black holes and maybe even dark matter. And so the big question is, how have galaxies evolved over time? How have they changed into what we see today? So the overarching field of cosmology is a huge field, but the quickest summary is that we believe the universe is about 13.9 billion years old. Everything started in a big bang. The universe was extremely hot. All there really was hydrogen and helium, and over time galaxies collapsed down and formed out of that material. And everything else that we know, all of the elements heavier than hydrogen and helium, are just 2% of all the other elements in the universe. And so, what are some common elements? I want a little engagement here. Just shout out any element that you can think of. Oxygen, that's a really good one. Carbon dioxide, that's a great molecule made of carbon and oxygen. What else? Carbon monoxide, so the individual elements, carbon and oxygen. What else? Give me a few more. Nitrogen. Sulfide. Ooh, that's a good one, yeah. So we have lots of different elements. We have oxygen and nitrogen that we breathe. We have neon and argon that we use to make glowing neon signs. We have aluminum, iron, things that we use to build buildings. Precious metals like copper, silver, and gold that we use to make pipes, make jewelry. And so all of these things seem very different, but they all have one thing in common. Every single one of these elements was made in a star. Every single element we know of, other than hydrogen and helium, was fused in the cores of hot stars over long periods of time. So Carl Sagan really summarized it best. We are literally all made of star stuff. And so as kind of an interesting bit of the roughly 80 some odd stable elements that we know of, how many do you think you brought with you tonight? 10, 20, 40? The answer, I heard it low, is somewhere between 60 and 70. And where are those? They're right here in your cell phone. All of the precious metals, the gold connectors, every bit of the aluminum case, whatever it is, your phone has most of the elements that were ever formed in the past 13.9 billion years, and you're carrying it around in your pocket. So how does this work? We have kind of two flavors of star formation. When a galaxy forms, we have these large clouds of gas that will collapse down, compress down. They'll begin to heat up as they compress under the force of gravity. And if it's a relatively small star, then it will compress down. It'll form a star very much like our sun, and it will begin to fuse hydrogen in the center. You're actually smashing hydrogen atoms together with enough energy that it can make heavier elements. They stick together and form heavier elements. Over time, it will run out of that fuel. It will puff off its outer layers and make these beautiful planetary nebulae, many of which you see on the wall here that were photographed by the members. If the star is a little bit more massive, then it can go past hydrogen and helium. It can actually fuse even heavier elements inside the star. And when it runs out of fuel, it can no longer fuse anything heavier. It basically runs out of the energy that's holding it up, and it collapses down and explodes in a supernova. And for a brief period of time, this single exploding star can outshine the light of hundreds of millions of stars in the rest of the galaxy, and in the process makes lots of these heavy elements. So the real key here is that all these cycles of star formation are making these heavy elements and then putting them back out into the galaxy. So if we want to understand the story of how galaxies evolved, we really want to know how their stars have evolved. And if we want to know how their stars have evolved, we have to look at what they left behind, which are the heavy elements in the gas of the galaxy. So there are lots of different chemical elements. You may have seen a periodic table, all the different ways these are produced. In astronomy, we like to keep it simple. We have hydrogen, helium, and we just kind of call everything else a metal. That would probably make some chemists and some material scientists not too happy, but you know, hydrogen, helium, and stars. What more do we need, right? So with this picture, let's go ahead and kind of put together the big picture view of the universe. So let's take the universe, let's put it in a box, and let's simulate it in some of the most powerful computers that we have and see what happens over time. So if we start at the very beginning of the universe, these individual dots of purple here, these are galaxies and whole clusters of galaxies. We're starting at the very earliest part of the universe when stars have just barely formed. And so there's not a lot of these heavy elements. There's not a lot of these metals. And so this is what we call low metallicity, basically very few heavy metals. And as we move towards the present day, stars begin to form, they go through their life cycle, and they eject these heavy elements back out into the galaxy and even beyond the galaxy. And we start to get these green regions, which we call high metallicity. Basically, we have lots of these heavy elements compared to what we had before. And so this is a really critical term I'll use a lot, metallicity. Basically just the amount of heavy elements that we have relative to hydrogen and helium. The last key point here is that we have all these different galaxies moving around, but for the most part, the universe is dominated by smaller, low-mass galaxies. So I'll use the term small a lot, but I mean low mass, meaning not a lot of stars compared to bigger, more massive galaxies. So the big massive galaxies, they're the easiest to see. They're very bright, they're very, well, very massive, and so we can see them much more easily with our telescopes. But as you go smaller and smaller, it's much more common to have a smaller, lower mass galaxy. But they're a lot harder to see. We need to have more powerful telescopes and deeper, more sensitive observations. And so since this makes up the majority of galaxies, this is really where we want to focus our attention. We want to understand what's happening in these smaller galaxies. So to kind of paint another picture, here's an example of two very nearby bright, beautiful galaxies imaged with Hubble. On the left, we have kind of a more edge-on spiral galaxy, and on the right, we have more of a face-on spiral galaxy. And each of these galaxies has a number of components that are similar. So in the center, we have the very nucleus of the galaxy, and around that, we have the bulge, which is basically kind of this roughly spherical shaped ball of older stars. They tend to be more yellowish, more stable in the center of the galaxy. And then we have these beautiful spiral arm features that wrap around the galaxy. And these regions are being lit up by the stars and the gas in the galaxy. And so they look like these kind of almost solid structures, but they're actually only a few more dense than the rest of the galaxy. There's just enough extra gas there to cause to basically burst into formation, just enough where we can get stars to rapidly form, and those stars excite the gas around them. They cause it to glow just like a neon sign. They ionize that gas. And so if we zoom in on one of these regions, each of these individual little blue dots is an entire star forming region with hot young stars inside that are ionizing, exciting this gas, and causing it to glow. So this is our first tool that we use to study galaxies. This is imaging. We open our telescope, we record the light, maybe we pass it through a filter to get specific colors, and this tells us where things are, tells us about the distribution, tells us about the sizes, but we can get a lot more information with spectroscopy. So a phrase is that if a picture is worth 1,000 words, a spectrum is worth 1,000 pictures, meaning we can get so much more information if we spread that light out and look at it more carefully. So the light that we see, the light that you see before you now, is a spectrum made up of many different colors, many different energies, many different wavelengths, and these ideas are all connected. So the portion of the spectrum that we see is the visible. You move from the blue end, which is higher energy, shorter wavelength, towards the red, which is lower energy, longer wavelength. And this idea sometimes seems really disconnected from the way that we perceive the world, because we don't seem to interact with it in the way that we might think. We can see the colors, but these ideas of energy and wavelength, it's not necessarily intuitive, but it really is. You interact with all of these things every day. If you think about the highest energy radiation, X-rays, we use X-rays to take images of our bodies, right? Because those high energy radiation can pass through your skin and tissue to get pictures of bones and pictures of teeth. As we move towards the longer wavelengths, we get to the UV, the ultraviolet. If you've ever been outside and gotten a sunburn, that's because the UV radiation is interacting with your skin and causing that sunburn. Then we have the visible portion of the spectrum that we can see. And as we move further out, we get into the infrared. For example, if you ever held your hand up to an incandescent light bulb and you feel the heat, it's because the infrared radiation is interacting with your skin, and that's how you perceive that light. We perceive it as heat. And you can go all the way out even further to microwaves. If you've ever heated up a piece of food, why do we use microwaves? Microwaves are longer wavelength, lower energy, so when they pass through your food, it causes the water molecules to vibrate, gives them thermal energy, makes your food hot. So this idea of the spectrum is just a continuation from one end to the other. You're going from high energy to low energy, you're going from blue to red, you're going from short wavelength to long wavelength. All these ideas are interchangeable. And so just to drive this home one more time, here's an example of a really hot piece of metal being forged by a blacksmith. If you had to take a guess, go ahead and shout out, which piece do you think is hotter, the white portion or the red portion? Right? Yeah, everyone said mostly the white portion, right? And that's because we literally have these phrases, right? It's white hot, it's red hot. So even without thinking about it, you can identify just based on the color of this material how hot it is, how energetic it is. And we know intuitively that as we move towards the darker reds, the longer wavelengths, the lower energies, that's not as hot. And so all these ideas are connected. So to bring this all together, how do we do this with galaxies? If you take light and you pass it through a piece of glass, the light will travel through the glass, it will slow down briefly, and then it will pick back up at the normal speed of light on the other side. However, if we take that light and we hit the glass at an angle, that light will spread out as a function of color. And so if we go ahead and we zoom in on this portion right at the interface of the glass and look at this in a little bit more detail, why is this? This is because light is interacting with the glass, just in the same way that light interacts in the ways that we're familiar with. And so if we take all the colors of the rainbow, and let's just for a minute, let's keep it simple, it's isolated to one color, let's say red. What happens is as those red wavelengths move towards the glass, they'll hit that surface and they'll briefly slow down. And so that bends the wavelengths of light as it passes through the glass. Now, if we take higher energy, like blue or violet, well, that's much more energetic. It interacts with the glass more aggressively, and so it bends and slows down even more. And so this light that was made up of all these different colors, all the colors of the rainbow, as they pass through this glass, they split up into different amounts. And we can use this to study the light from galaxies and stars and gas. So how does this work in practice? There are two main types of spectra that we can get. The first is basically a continuous spectra. If you take a hot object like the sun or any other star or that glowing piece of metal and you take a spectrum of it, that light will spread out and you'll get light at all the different colors, at all the different wavelengths, because it's a hot object. It's producing a variety of energies. That's in comparison to something like a fluorescent light bulb or a neon sign. And those are different because they're filled with gas. And when you pump electricity through that gas, it excites it. It causes it to glow, just like you see in a neon sign. It has individual atoms with electrons that get excited, they jump up and down, and they only release light at very specific wavelengths, very specific colors, because they only have these very specific jumps that they can do. And the key is that each element has this unique fingerprint. Each element has a different spectrum, and so we can use the spectra of galaxies and stars and their gas to understand what's there, to understand how much of it is there. And so what can we really learn in detail? There are three things that I'll use a lot tonight, so I really want to show them up front. The first is the mass of the galaxy. And so as I talked about, it's basically the mass of all the stars. We have small, low-mass galaxies, and we have big, high-mass galaxies. A low-mass galaxy might have 1 million or 10 million times the mass of our own sun in stars. A really massive galaxy might have billions of times the mass of our own sun in stars. And there's really nothing special about the sun except for the fact that it's really nearby, so we can measure it very precisely, and so we use it as a ruler in astronomy. We measure the masses of things in terms of the mass of the sun. We measure the brightness, the luminosity of things in terms of the brightness and luminosity of the sun. We measure temperatures, all these sorts of things. And then as time goes on, we realize they're all changing. But we use it as a ruler. So we use it to measure the mass. We can use it to measure the star formation rate, the rate at which stars are currently forming in a galaxy. So in the picture I showed, these stars light up these gas clouds and cause them to glow, just like that fluorescent light bulb. And we can say, okay, well, the more rapidly it's forming stars, the more it's going to light up that gas. And so we can use it to actually measure how fast it's forming stars. And the last one is the metallicity, which we talked a lot about, the overall abundance of these heavy elements compared to hydrogen and helium. There's another really key piece that these emission lines give us. These emission lines are at a specific wavelength, specific color, specific energy. However, there's the Doppler effect. If something is moving toward or away from you, those wavelengths will get squished or stretched out. Just like when you hear a loud truck go by with a siren, it's very high pitched as it approaches you, and then that pitch begins to get much lower as it passes you, because those wavelengths are getting stretched and squeezed. And so this is the idea that if something is moving away from you, it is being redshifted to longer wavelengths, and if it's moving towards you, it's being blue shifted to shorter wavelengths. And so what we see in the universe is that basically almost all galaxies are moving away from us. With the exception of the ones that are really, really close to us, they're pretty much all moving away. And the further away they are, the faster they're moving away. And so this is called Hubble's law. The universe is expanding, and the further away things are, the faster they appear to be moving. And so if we measure how fast a galaxy is moving away from us, we can figure out how far away it is from us. And that's really important. If you want to understand how bright something really is, you need to know how far away it is. If I take a flashlight and I run away with it, it's going to get fainter and fainter. You can only tell me how bright it really should be if you know how far away I am from you. And so just to highlight this one more time with a little bit of an image, if a galaxy is moving away, all those colors that we saw, they get stretched or compressed to different wavelengths. So we can use this to understand what galaxies are doing. So with that, you have all the tools that you need to understand what's happening in galaxies. So what has been done so far? Where are we at, and where do we want to go? So what have we learned so far? There have been a huge number of studies on galaxies. I'm not the only one doing this. There are many other astronomers. There's been many astronomers in the past. Lots of folks are working on this. But if I had to pick one piece to highlight, it would be the Sloan Digital Sky Survey. And so this is a survey using a 2.5-meter telescope in New Mexico. I've been fortunate enough to visit this. It's about the size of a school bus. And what they did is to try and get images and spectra of as many galaxies as they possibly could. So this is not the biggest telescope in the world, but it's a dedicated survey instrument. So night after night after night, they use it to look at galaxies. So in the first step, you take an image of the sky, and you locate those galaxies, and now you have an image. You know where those galaxies are, you know how big they are. The next piece is to get a spectrum. And so what do you do for this? You want to get a lot of galaxies all at the same time. So what you do is you make about 5,000 of these metal plates. And it's a little difficult to see, but this plate has about 600 little teeny tiny holes in it. Each hole is the location where someone would take an optical fiber, plug it into that hole, and then when they point the telescope at the sky, the light from each galaxy will go down an optical fiber into the spectrograph, and they get spectra for hundreds and hundreds of galaxies all at the same time. So with this, we've been able to measure these very key parameters of galaxies, their masses, their star formation rates, their metallicities. And for the most part, these are galaxies that are kind of in our own local part of the neighborhood. There are some more distant ones, but because you can only stare at it for so long, and there's a relatively modest-sized telescope, the majority of the galaxies are the ones close to us, basically the universe as it is today. And so what do we find? Well, what do we do in astronomy when we want to learn anything? We make a graph, right? You measure as many properties as you can, and you start making graphs and see what pops out. And so one of the more interesting things to come out of these studies is what we call the mass-metallicity relation. It's the connection between the stellar mass of a galaxy and how much metal has been produced and is in that galaxy. So what we're looking at in the top right here, these are our really big, massive galaxies. And then as we move towards me, to your left, those are the smaller, less massive galaxies. And then moving up and down here is the amount of oxygen, or in this case, the metallicity. And why oxygen? So I love that the first element shouted out was oxygen, because it turns out that oxygen is about half of all the heavy elements in the universe. And it produces really bright emission lines. It makes those very distinct spectra, and so it's easy to trace. So we use oxygen to kind of trace the overall abundance of all these metals. And what we're looking at here, these kind of big contour regions, these are averages of tens of thousands of galaxies. And if you kind of take an average all the way across, you get this red line here. And so what is this? The orange line shows you the metallicity of the sun. And again, there's nothing super special about that. It's a very precise quantity that we can measure. And so when we go to compare measurements with other astronomers, we're all using the same ruler. We're all using the same 0 point. And what we see is that these really massive galaxies have a lot of oxygen in them, more than the oxygen of the sun. So they have a very high metallicity. And then as we move down to these smaller, less massive galaxies, they have much, much less oxygen in them. And so there's a lot of different ways you could possibly explain this. The kind of two most common ones are, well, these small galaxies, they don't have a lot of mass. Their actual gravitational pull is smaller than these big massive galaxies. So as the stars eject these metals in these energetic events, they can basically escape beyond the galaxy and move out into the gas that's between galaxies. The other possible interpretation is, well, they're really small. They're still building up. They're still growing and still forming their stars, and so maybe eventually they'll have these higher metallicities. There's one more piece to add into this. You can say, okay, well, this looks like a great fit, right? It's a line, matches up, but there's still galaxies all above and below this. So it's saying, okay, well, it looks like they're connected, but there's still kind of a lot of dispersion there, a lot of uncertainty in there. And so what do? We start looking for another property. And in this case, the third one is the star formation rate. So now we're looking at the same thing, except we've color-coded the galaxies based on how fast they're forming stars. And so what we see is that these galaxies that are very slowly forming stars in red, these have very high metallicity. They have lots of oxygen in them. As compared to these galaxies more towards the bottom, they're very rapidly forming stars, and they have much less oxygen. And that actually might be kind of counterintuitive, right? You say a galaxy is forming tons of stars, like it should have a lot of oxygen. But it's a time scale thing. So if you look at a galaxy that's very slowly forming stars, it may have formed lots of them in the past, and they've released all their oxygen, and now there's not a lot of fresh hydrogen and helium to form new stars. Whereas these ones down here, they're rapidly forming stars right now, so there hasn't necessarily been enough time for them to die and release their oxygen out. One other possible interpretation is, well, if you smash some galaxies together, you add a bunch more hydrogen and helium, and you trigger a lot of stars, and so that's one other possible way. So there's lots of explanations of this, but the key is that we see this very clear trend from one side to the other. It tells us that these three things are fundamentally linked, and we actually call this the fundamental metallicity relation. It tells us that the amount of stars and the amount of metals in the galaxy and the rate at which it's forming stars are all tied together. It's all connected. So that's where we stand today. We say, okay, we have this really nice, interesting connection between these properties, but this is mostly for the galaxies just in our own part of the kind of local universe. So what does it look like if we look into the past, if we look at more distant galaxies? And also, on top of that, what does it look like if we look at even lower mass galaxies, the smallest possible galaxies that make up a huge population of the galaxies that are out there? So in order to do this, we need new observations of really faint galaxies, really distant galaxies in order to answer these questions. And so, of course, the question is, where are we going to look? What kind of telescopes are we going to use? And for this, we want to understand where we should look. Where should we target in order to look at our galaxies? And so this is basically a graph of the average rate at which galaxies are forming stars over the course of the universe. So over here on your left, this is the amount of time since the universe formed. So here at 0, this is today. And what we say is, on average, galaxies are forming stars at some rate. And as we go back in time, billions and billions of years, with a gigayear being a billion years, we go back in time to about 10 billion years ago, galaxies on average are forming more stars more rapidly. And as you keep going back to basically the earliest times in the universe, it slows down because galaxies just haven't had enough time to start forming stars yet. So if we want to understand when these connections got set up, we want to look right at the peak. We want to look at when galaxies were most actively forming their stars, when they were most actively building up their stellar mass and their metals. So how are we going to do this? Well, we need some really, really deep data. And so we use two telescopes in particular. The first one is the European Very Large Telescope. That's the name. It's a series of 4 telescopes that can all be combined to do a bunch of really incredible imaging and spectroscopy. Now, when you ask for time on a telescope, you have to justify how much time you need. You say, okay, I want to look at this galaxy or these galaxies, and I think I need an hour or 2 hours or 5 hours, depending on how faint that object is, depending on how far away that object is. Well, we want to look at some of the faintest, smallest galaxies out there. So our team, led by Michele Fumagalli and Mark Revalski, they asked for 150 hours, which is tied for the biggest program that's ever been awarded on this telescope to point at a single patch of the sky. This telescope gives us the very blue portion of the spectrum. We also want to get even longer wavelengths, even redder colors, because we need all of these different emission lines in order to understand what's going on with these different chemical elements. And so for that, we go to the Hubble Space Telescope. Hubble is above the atmosphere, so it can look at even redder wavelengths, and it can let us probe things in really, really great detail. And so in a similar vein, we were awarded 90 orbits with Hubble, which is roughly the largest program to stare at one patch of the sky with a single instrumental setup. So it's a lot of time. So these two data sets together, what did we get? What did we do? So let's go ahead and look at an image that we obtained. So this is the patch of the sky that we looked at. We chose this patch for a reason. I can talk about it more later if you're interested. But just like we saw at the very beginning, almost every dot in this image is a galaxy. There's a couple of foreground stars in our galaxy, but for the most part, every single dot here is a faint distant galaxy. And so the very first step is we need to locate our galaxies. So in astronomy, I love using a telescope, but really we spend a huge amount of our time on computers doing computer coding in order to understand the observations that we're looking at. And so the first step is to write computer code that will go in and identify the galaxies, measure their sizes, measure their shapes, measure their orientations. And when we do that, we get something that looks like this. Basically now, the computer understands, okay, each point in this image is something that we're interested in studying. The next step is to do our spectroscopy. Now we want to take that light and we want to spread it out as a function of wavelength. And there's a couple different types of spectrographs. There's some that look at one galaxy at a time. There's some like Sloan that can look at many, many galaxies at a time. This particular one for Hubble is called a slitless spectrograph. And the idea there is we don't necessarily know ahead of time where every single galaxy is going to be. So we want to get as much data as we possibly can. So what do? You take the entire image and just pass it through your spectrograph. You disperse the entire field of the sky. Each one of these lines is a spectrum of a galaxy or a star. That's awesome. The flip side is you might notice that this is a bit of a mess. We have spectra that are overlapping and running into each other. And so what we do is we take the observations at different angles with the telescope. So that way if light runs one over one galaxy on another, when you rotate the telescope, now that doesn't happen. And so we use this to get spectra of thousands and thousands of galaxies. And so I want to show you what the real data actually looks like. So on the left here, this is the spectrum that we get from the ground-based telescope from MUSE, and on the right, that's what we get from Hubble. And they look somewhat different because they have different instruments, different characteristics, but basically over here we're getting the very blue portion of the spectrum. These are the wavelengths that our eyes are sensitive to, and then as you move further with Hubble, you get into the red, into the infrared, and so we can stitch these two data sets together in order to understand what's going on. So I talked about before, each element has its own unique fingerprint, its own unique chemical imprint on these spectra. And so I've kind of zoomed in on some of these lines here, and each one is labeled from what it forms from. So we have lines from carbon, lines from oxygen, lines from helium, lines from silicon, lines from magnesium. And the numbers are basically just where we expect them to be, and then we measure them where they actually are, how much they've been redshifted, and that tells us how far away the galaxy is. So how are we going to use these data? Let's go ahead and look at another spectrum. Lots going on, but let's look at just the lines from oxygen, because that's the element that we're interested in tracing. And we actually get several lines from oxygen, from different energy levels and things like that. And we have kind of two sets of lines. We have these really bright lines, these lines that produce a lot of light that are relatively easy to measure as compared to some of the other ones. And then we have this one in the middle, this little faint one. Now, what's our goal? Our goal is to determine how much oxygen is in each of these galaxies. There are two ways to do that. The first one we call the direct method, for lack of a better term. Basically what it means is you use these spectra to measure the temperature of the gas. That tells you how excited it is. And that tells you how much light each oxygen atom should be producing. So you measure how much light you're getting, you convert that into the amount of oxygen that's there. However, as you might have guessed, the line that we need to do that is this little teeny faint one right here. And so unless we have really, really deep observations, even for some of these smaller galaxies, we just can't see it. Our data are just not sensitive enough to get that emission line. So we can also use these very strong lines. And so we call this the strong line method. However, it's a little bit more indirect. You're kind of stitching together multiple pieces of information. In galaxies where we can use this one method, then we say, okay, well, how strong are these other stronger lines? Then when I don't have that weak line, I'll just use the strong ones. But the problem is there's some assumptions in there. It means that you're hoping that the galaxies you're looking at are the same as the galaxies that you were looking at before to some extent. So hold on to that for a minute, and let's look at the actual data for our field. So these are a bunch of different spectra. Basically what we're looking at is the dispersed light from those galaxies, and then I've split it up as a function of how massive that galaxy is. So up here at top in brown, these are the really big massive galaxies, and as we move on down, we're getting to the smaller and smaller and lower mass galaxies. And at first glance, these kind of look pretty similar, right? But there's a lot of information in here. You notice that some lines coming from oxygen, for example, look about the same, whereas other lines get stronger and stronger or weaker and weaker, depending on how massive that galaxy is. Same thing for some of the other lines. They start out very strong, and then they get weaker and weaker. And so this is telling us that there's something changing as we go down to these smaller galaxies. As we're going to find out, there's a lot changing. So the very first step is, okay, well, we want to make sure that our methods are accurate, right? If we're going to go ahead and try to measure the amount of oxygen in thousands of galaxies, we need to know that the tools and techniques that we're using are actually correct. And so what I mentioned just a moment ago is that there's kind of two ways to do this. The first is this very direct method, this very accurate method, but it requires very faint little lines. And then we have this secondary method based on just these very strong emission lines. So what you do is for the galaxies where you can detect those little faint lines, you use both techniques and see if they agree. So basically what we're looking at is the amount of metal that we predict from this very accurate method and the amount of metal that we predict using this secondary method. And if they agree perfectly, they should fall right on this solid black line. If they fall within the dashed lines, that's pretty good. Within the dotted lines, it's pretty good. And outside of that, we say we have a problem. They don't agree. So when we do this for our galaxies, for the dozens of galaxies that we can, we see pretty good agreement. Believe it or not, in astronomy, this is incredible. So the points are very close to this one-to-one line. And even though we have some pretty big error bars because these are really faint, distant galaxies, on the whole, they all sit within this strip that tells us that these two techniques agree. And this is really important. If you take one piece away from this, it's saying that the techniques that we used for galaxies that are very close to us work for galaxies that are much further away. The galaxies in blue represent galaxies as we saw them nearly 6 billion years ago. The ones in orange represent ones nearly 10 billion years ago, when the universe was basically just 20% of its current age, looking 80% of the way back in time. And it's telling us that these techniques work. So now we can apply this to thousands and thousands of galaxies, even if we don't necessarily have all the information that we otherwise might need. And so what have we found? Well, the result we looked earlier was this mass-metallicity relation, this connection between the mass and the amount of oxygen in galaxies. So let's look at that now. So what we have here, all of these different colored dots, these are other people's studies looking at galaxies at similar distances, looking billions of years ago. While these dashed lines here, those are the results that were found for the galaxies that were very close to us. And there's two pieces to take away from this. The first one is that we added this data point right down here. So we did a whole lot of work and we got one data point. But that data point is really important because we're looking at lower and lower and lower masses. And so that point represents galaxies that are 5 times less massive than have ever been able to observe and characterize the metallicity before. So not just, 10 or 20%, 5 times less in mass. So now we're getting down to these really small, really faint galaxies that make up most of the galaxy population. And what we see is that the amount of oxygen is still going down. It's even lower than these other galaxies. And that's really important because eventually this has to stop. Eventually you'll just have nothing but hydrogen and helium. All these galaxies we see, they have stars. That's how we're able to see them. And so they have just a little bit of oxygen. Turns out to be less than 10% of the amount that's in the sun. And yet it's still going down. And so this is a really important constraint because it tells us that we need to go even further. The second piece is that we see that all of these studies are sitting below these lines at what we saw in the local universe, meaning all of these galaxies have, on average, about 2 times less metals than the ones that are nearby us. And so what that tells us is billions and billions of years ago, on average, these galaxies had about half the amount of oxygen. And that sounds like one data point, but it's really 3. We know the amount of oxygen galaxies have now. We know that they started more or less with none, and we know at some point in time they had formed about half of it. So we know the other half has formed since then, and the other half had to form before then. So that's a really interesting constraint on looking at galaxies billions and billions of years ago. So let's start to bring this all home. So the first thing we did is that we measured the metallicities of these very small, low-mass galaxies billions of years ago as they appear to us today. When we did that, we first tried to use this very accurate, very well-known, very well-calibrated technique, and we found that it still works even if we make these other assumptions for these secondary techniques, which means that we can use these techniques to look at galaxies over a wide range of ages, over billions and billions of years of cosmic history. Now we know our tool works, and so let's go ahead and keep using it to do even better studies. The second piece is, as we go to these lower and lower metallicities, these galaxies are still going down. They still have less oxygen than these more massive galaxies. And eventually, this has to flatten out. This has to stop, because otherwise we just have pure hydrogen helium. And so this is a really important data point to compare with computer simulations. In computers, we can run almost anything we want. We can simulate galaxies, even galaxies that we can't yet observe. And so knowing that these very small galaxies have very little oxygen helps us constrain those simulations. When we look at galaxies that we've run on the computer, we say, hey, do they agree with what we saw with these really deep observations from the ground and with Hubble? So I'd like to wrap up with just a little bit of a peek into the future. Where are we going next? What do we want to do now? If that wasn't enough, yes, we want to keep doing more. So the answer is the James Webb Space Telescope. This image shows a comparison in size relative to an average person of the Hubble primary mirror and the James Webb Space Telescope primary mirror. Hubble is about 2.4 meters, whereas Webb is 6.5 meters. And what that means is it can gather much more light much more quickly, and so we can see much fainter galaxies. Now it's important, Webb is not a replacement for Hubble in any way. It's specialized to look at these even longer, redder wavelengths so we can look at galaxies even further back into the past. And so really we need both of them working together in order to build up the full picture of what's going on. But now we have Webb, which is specialized to look at even further away, even younger galaxies that we just couldn't necessarily see. And so to highlight this, this is an image of some very nearby galaxies, a very famous known cluster of galaxies, and this is an image with Hubble. And if we fade to the image with Webb, maybe kind of instantly you don't see like these really huge differences that you might expect. There's a couple of reasons for that, the way that the image is put together, but where Webb really shines is when we look at even more distant galaxies. So let's zoom in on this little teeny tiny corner of the image. In the center here, we see kind of one galaxy with some spiral arms from our Hubble image, and there's these really little faint, teeny tiny dots around it. If we look at this same region with Webb, all of a sudden, we see these galaxies just start to pop out. Now we can look to those longer, redder wavelengths even earlier in the universe, and we can start to see these galaxies at the earliest periods in cosmic history. So my main takeaway message, if you remember just one thing from tonight, is that by studying distant galaxies, we can understand how the chemical elements that make up everything that we know, everything that we are made of, were formed over billions of years of cosmic time in the hot cores of stars. And with that, I'd be happy to take any questions. Thank you. Lots of questions.
What if all these models are wrong? What if the universe is older than we think?
So fantastic. So the question was, what if some of our models are wrong? What if the universe is even older than we actually think? And that's a great point, because the models that we have for lots of things in astronomy, including kind of the overall history of the universe, they work really, really well in predicting certain things that we can observe. However, there's some other places where they disagree, and they can't actually necessarily predict everything we observe. So the whole kind of age of the universe, the big picture scale of things, we think we have a pretty good understanding of that. But with James Webb, we're going to be able to test that even more and more, because now we can look at galaxies at that critical moment when they're just first starting to form. And so I've kind of dodged your question there a little bit. The answer is there could be issues, and we're going to learn a whole lot more about it very, very soon.
It could be all wrong. The universe could have started in a completely different way than we think.
There are certainly times in astronomy when we thought we had it all figured out, and then we realized that it was a much bigger, different place than we thought. So absolutely, that is a possibility.
So how could galaxy metallicity be used predictively? Any useful data?
Okay, so the question is, how can you use the metallicity in a predictive power? How can you measure the metallicity and then use it to, say something useful going forward? One of the key ways that you can use this going forward is that after these stars die and they expel all these elements out into the galaxy, that gas doesn't just sit there forever. Eventually, that gas can cool and form into new generations of stars. And now those new stars are not just pure hydrogen and helium. They're hydrogen, helium, and traces of all of these heavy elements. And that's really important because it changes the entire way that the star evolves over time. It changes how massive the star can be, it changes how long that star can live, it changes its brightness, its luminosity, its color, everything that you see on the wall here, all of these different stars, different sizes, color, shapes, all of that will change when you add more of these heavy elements into it. That's one example of how it can be used predictively moving forward. Questions?
So every, oh, I'm sorry.
No, please.
Every once in a while in the news, you hear about a novice stargazer who has identified a new star, a new something. How often do you think that actually happens? And like, what are the odds that someone in this room, within the next, like, let's say month, would see something that has not previously been identified?
For sure. So, the overarching question is, there's all these reports of amateur astronomers finding something extraordinary, something that's been missed. What are the chances of going out and doing that yourself? The chances are actually really good. It depends the way that you go about it. So for example, there are lots of times in astronomy where it's really hard to get telescope time to do something very specific. And there are times when all these quote-unquote amateurs, I use the term amateur very loosely. The only difference between amateurs and professionals is whether or not you get paid, right? So there are amateur astronomers who can go out and they can look at something night after night after night after night. And a huge majority of the supernova discoveries in nearby galaxies, of these stars that have exploded and are creating all of these elements, the vast majority of those years ago were done by amateurs looking at the same galaxies every night by eye and saying, hey, this galaxy looks a whole lot different than it did yesterday. And then they ping the astronomers and say, go point everything you have at this. There are lots of other examples. Detecting comets that have, are going to careen and crash their way into the sun, in which case I believe you still get to name it. All sorts of examples like that. There are lots of big galaxy zoo and public projects for people to go out, look at images, and try to identify things that are unique that might have been missed otherwise. And a lot of that is being used behind the scenes in an incredibly powerful way. A lot of it is being used to train our computers. So when you go to a website and it says click all the boxes with with streetlights in it, it's checking to make sure that you're a person, but you're also training the computer what a streetlight is. When you type a sentence in a box that says type this sentence to prove that you're a person, you've transcribed a piece of text that a computer did not know how to read. And so when people go out and look at these images and classify galaxies, say this is a spiral, this is this type is merging, now you feed that information to a computer, and now the thousands of images that you've classified can be used to classify millions in a very short amount of time. So the impact can be massive.
Thank you.
So I think next one was up here, and then back there.
Yeah, so you have two really interesting graphs. The first one was like this bell curve, where you said the peak was 10 billion years ago, like the most galaxies formed. And then you said Earth formed at like 13 billion years ago.
So sorry if I misspoke
sorry,
there.
could you repeat that?
So roughly 10, so the question was kind of the time scales of how things have formed. So yes, so our best guess of the universe is about 13.9 billion years old. And after a few billion years, 10 billion years ago, on average, galaxies were most rapidly forming their stars. And so at this point, this is when galaxies are forming stars very rapidly, and then over time, releasing those metals. I don't have a good number off the top of my head for exact formation time of the Earth, but I believe it's something around 4.5 billion years, which means there was time for those metals to be incorporated into the Earth and planets.
Yeah. So the reason I asked was like there was another graph after the one that like looks like an inverted log curve, where you said older galaxies have lower metallicity. It was towards the end.
Okay, so is it? Oh, maybe I missed it.
I think it was one of the last few slides that,
So I'll leave it there. Yeah. So,
okay. Yeah, I
so
wanted to ask about the relationship between those two graphs. Because if you're saying that most galaxies form at that like peak of the bell curve, that there's, yeah, this one, the oldest galaxies have the lowest metallicity, then,
so oldest meaning looking back furthest in time. So they are actually, if you will, the youngest galaxies that we're observing. So they're the ones we can see furthest back in time. So I apologize if I misspoke there. So these galaxies that we're looking at, we see them as they were billions of years ago, and so we're seeing them at a much earlier time as compared to the galaxies today. Great questions.
Mitch, to that point, that same concept, right, like what you're seeing that's further away is an older stage of what that is in the present day. Can you predict to any certain degree now what that galaxy looks like, even if it's light that's very old, as you're saying?
Yeah. So the question is, can we kind of piece these things together by looking at galaxies far away and nearby in order to understand what's going to happen to them? And so this kind of goes back to the predictive power. We say, okay, well, we can look at galaxies today, and we know, some of their properties, their mass, their star formation rate, their metallicity, and we can look at these galaxies billions of years ago and measure those same properties. And what it can really tell us is how mass builds up over time. It tells us how long it takes for galaxies to form huge generations of stars, for those stars to die, and then for those stars for new stars to form that have incorporated those metals. So we can look at these galaxies and say, okay, they have half the amount of oxygen 10 billion years ago. Give or take, with some uncertainty, we know that in that next time leading up to today, it has to form at least that much more again. So you can use these pieces to kind of piece together what's going to happen. Now, for individual galaxies, all bets are off. Galaxies crash into each other. Some galaxies are off on their own. Galaxies are in huge clusters interacting. So for an individual galaxy, it's very hard to say. But on average, we can start to predict what they're going to look like. So we have lots more questions, and I'm happy to keep chatting after. If you'd like, we can go ahead and pause the recording there and then keep doing questions, or I can keep going if you like.
Are there any further questions?
I have one. Art, so you mentioned small low-mass galaxies are more common. Are any of those within range of like an 8-inch telescope here, or do you always need Hubble and Sloan to see them? Like, could we see one if the full moon wasn't out tonight? Could we see one in a telescope?
Certainly. So the question is, can we see some of these smaller low-mass galaxies even just in a smaller telescope like an 8-inch that we have here? You certainly can, but you have to look for the very, very nearby ones. And so we'd have to go a little further south to see things like the Magellanic Clouds, which are examples of these dwarf galaxies that are going right around the Milky Way itself. But there are other examples. If you go look at, for example, M31 Andromeda, one of our favorite galaxies, just down near it, there's a little fuzzy that looks like a star. But it's not a star. It's actually a much smaller galaxy that's much, much smaller going around Andromeda. So that would be a good example of one of these smaller low-mass galaxies.
Like Messier 110 or M32?
Yes, I believe,
Yes.
you know better than I believe that's the correct Messier number.
Great, thank you.
I think there's one patiently waiting over here.
I'm asking another two questions. So I know that the Milky Way and other large galaxies are eating up small galaxies. Does that decrease the ratio of small galaxies to large galaxies, or does it not matter?
So the question is, small galaxies are falling into big galaxies. Does that change basically the ratio of the number of small galaxies to big galaxies? It does. The answer is it does, but it's taking a really, really, really long time to do it. So we see all these galaxies today, and there's still tons and tons of these small galaxies. And over time, a lot of them will merge into these bigger galaxies. But it's on these timescales of billions and billions and billions and billions of years. But the short answer is yes, it is changing.
Oh, and can we extrapolate to the future? For example, what about 4 billion years into the future? Can we extrapolate what the Milky Way will be like?
So the question is, can we extrapolate what things are going to look like 4 billion years in the future, for example? And yes, we can to some extent. And a lot of it comes back to these properties we can measure, like velocity and distance. So we know that our galaxy and the Andromeda galaxy are actually moving towards each other. And in the course of billions and billions of years, our galaxies will actually merge together. And it's kind of crazy because you think, two things hitting into each other, it's going to be this crazy process, and to some extent it will. But the spaces between stars are humongous. So you might have hundreds of millions of stars, and how many you think are going to actually collide and hit? The answer is like 3 or 4. It's not that many stars. So the galaxies will pass through each other, go through all these crazy interactions, and then merge to form a bigger star. So I think we have one more up here before we cut it. Yeah.
I lost a tooth.
You lost a tooth. All right. I feel like I should have been prepared for that. That's awesome. Congrats on your teeth. One more?
There's a question back here.
There's a question in the back.
Go right there. Did you have your hand up before?
I did, but you kind of answered it, so.
Okay.
Great. Well, before we cut it, thank you so much again, everyone, for making the time to be here tonight. Before you depart, I'll be happy to stick around and answer more questions. Do please be sure to come up. I have some nice materials up here from the Office of Public Outreach and Space Telescope. We have some really nice posters from James